All right, today, as promised, I want to start off with the Chutes and Ladders simulation that I made in Mathematica. Of course, Chutes and Ladders, the game, that's one of the first games I ever played when I was a kid. That's what the old board looked like a long time ago. It's been updated. That's kind of what I remember. And there's a spinner that spins 1 through 6. You don't start on square one, because if you did, you'd go up the ladder to square 38 right away. So you start off the board and you spin the spinner. If you get a 1, that's great because you go up to 38. If you get a 2, then you land there. 3, land there. Get a 4, you land there. You go up this ladder to 14. Did I call this ladder a chute? It's a ladder. Or 5 or 6. When you ladders are good because you go up. Chutes are bad because you go down. And you're trying to get to the end, be the first person to get to the end. And it's kind of dangerous up near the top because there's lots of chutes up there, meaning it makes it a little difficult to get down, to actually finish the game because of that. You go up ladders when you supposedly do something good, and you go down chutes when you do something naughty. How can this possibly be simulated, and why would we want to simulate it? Well, I wanted to simulate it just because I was interested in it. And it seemed necessary to simulate it because it's like hard to think about theoretically. You know, the chutes and the ladders are in kind of random places and they go up or down kind of random amounts. Yeah, you have a spinner that spins 1, 2, 3, 4, 5, or 6 with equal probability. But how in the world do you account for the chutes and the ladders? Well, you do have to keep track of where they are. So the first ladder goes from spot 1 to spot 38, then the second one from 4 to 14, the third one from 9 to 31, etc. And the chutes go down. 16 goes down to 6, 47 goes down to 26. The really bad one is, where is it? 62 goes way down to 19. That's when you really do something bad. Can this be simulated? I made what seems to be a pretty good simulation to me. I think it works. And what I'm interested in is the distribution of the number of spins to win, right? How many spins on average does it take you to finish the game? And what I found is on average, it takes around 30 spins to win the game. Of course, you're playing against somebody else, so they might beat you, but that's what the average is. So I'm using Mathematica here to simulate this. And the first function in Mathematica that I created, I called chute ladder, which keeps track of all what happens when you go up ladders or down chutes. I had to use Mathematica's which function, which is essentially a big piecewise function. Essentially, this syntax says if x is 1, then the output's 38. That represents the ladder going from 1 to 38. If x is 4, then the output is 14. That represents the ladder going from 4 to 14. Down here, if x is 93, then the output is 73. That represents the chute going from 93 down to 73. If x is greater than or equal to 100, we effectively stop. We keep the output at 100. Actually, the output wouldn't get bigger than 100, so I didn't really need to put greater than or equal to there. And if x is less than 100, but now one of these other ones, evidently, because you sort of go through this which command in order, then I keep the output at x. And effectively, this is just trying to keep track of the chutes and the ladders. But the 100 there means also that when you get to 100, you stop. The output is 100. So I enter that, and we can, for example, see that it works. Chute ladder of the input 49, for example. I see when x is 49, I should get an output of 11. Yep. And if I put in, say, 50, there is no chute or ladder that starts at 50, so the output should be x itself. It should be 50. I stay where I am. So this doesn't represent moving when you're at a tile that is not the start of a chute or a ladder. Staying there, but I need to spin as well. Spin and move takes into account the fact that you're going to flick the spinner and get 1, 2, 3, 4, 5, or 6, and then move as well, not taking into account chutes and ladders. So notice this function, spin and move, takes an input x and takes that value of x and adds, hey, there's random variate. Random variate, discrete uniform distribution 1/6. That's spinning, right? 1, 2, 3, 4, 5, 6 all occur with equal probability. Of course, we could use a die as well instead of a spinner. Discrete uniform distribution, those numbers 1, 2, 3, 4, 5, and 6 all occur with probability 1/6. And random variate is going to then simulate sampling from that distribution. And I'm adding it to x. So, for example, if I plug in 5, the output is going to be 5 plus some random number between 1 and 6 with equal probability. So it could be, the answer could be 6, 7, 8, 9, 10, or 11 with equal probability. But you're never going to get something less than 6 or more than 11 here. I can keep re-entering it. By the way, if you do a colon equals like that, that'll help you get different things when you re-enter stuff like this. Actually, there an equal sign would do the same thing, but there's other places where it's safer to do a colon equals. Okay, never get more than a 11 or less than a 6. Full turn combines the two. So I'm at location X. First, I'm going to spin and move. I'm assuming I've already done the output of a chute or a ladder, and I'm now at location X. I'm going to spin and move first, and then plug it into chute ladder. If the output of spin and move is at a spot where there's a chute or a ladder, then you apply the chute or ladder and you move. If it's not, then you stay where you were, right? That's why I have the output be X if it was not one of these. This represents staying where you are. So for example, if I apply full turn to 50, for example, or maybe I should do it to say 48. Why did I pick 48 here? Because I know that at 49, there was a chute going down to 11. The output could be 50, 51. It could not be 49. Because if spin and move brings me to 49, then chute ladder brings me down to 11. There's no way I'm going to get 49 here. I might get an 11. I got a 67. There must have been a ladder that went up as well. Come on. There's an 11. One of the outputs was 67. What was it, 67? That must have been some ladder. Yeah, if you get a 51, you go up to 67. Now I can iterate full turn with something called nest list to simulate playing the game by yourself. Init position means you're just starting off the board at position 0. Nest list is going to iterate this full turn function based on an initial position that I'm picking to be 0, so it's the start of the game. But I could pick something non-zero to simulate starting at some other spot. There we go. I did 50 iterations. And wow, that was a quick game, actually. The game was won in 1, 2, 3, 4, 5, 6, 7, 8, 9 spins. Wait a minute. There must be some error here because there's no ladder that goes up to 100. There's some error here. Okay, I've got to fix something somewhere here. The ladder goes 80 to 100. Does it really? Does it go to 100? Yeah. Wow, I forgot that. So if you land on 80, you win. Okay. So the next spin here brought you to 80, 74 plus 6, going up to 100. So yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, please. 9 spins. That's a pretty quick game. There it took more. Here it took even more. But it does seem like if you keep entering this, you definitely win within 50 spins at some point because you keep getting 100. Actually, if you use nest while list, you can stop it once you get to 100. Essentially, this is going to apply full turn until you get while you are less than 100 effectively. Once we get to 100, it stops. That game took a long time. So this is simulating a game and stopping once you reach 100. So The length of this list represents the number of spins, actually -1. I should subtract 1 from this. So now I'm using table to essentially do this over and over again and find the length of this list, which is the number of spins, except I have to subtract 1 from it because effectively I need to take off counting the 0. That's some data. I can look at these data. I can make a histogram of it. I can calculate the mean, and I can calculate the standard deviation. So there's a histogram of the number of spins to win the game. For example, this first one says there were this was a simulation of size 1,000 simulated games. Looks like 12 of them won the game within, what would this be, about it's not clear, it's not going down to 0 there, somewhere between maybe 2 and 8 spins. About 98 of them, if you can't see that number, it says 98. 98 of them took between about, maybe it's about 8 and 14 spins. The mode is somewhere between about 20 and 26 spins, but the mean is bigger. The mean's closer to, well, the mean for this simulation is 30.5 because it's a long right tail. And I could do this over again. I think if I re-enter this even as is, because I did a colon equals here instead of an equals, I think it'll redo the simulation and give me a different graph with a different mean and different standard deviation. Yep. But not too different. Okay. Question, are there any well-known distributions that are a good model? I don't know, I haven't tried. But you need a density function, a PDF that has a graph that goes up and then down about like that with a heavy right tail, a long right tail. Some sort of gamma distribution, perhaps, maybe something to guess as one possibility. Maybe something simpler, a sub-distribution, a chi-square. That might be too simple. 2 parameters is probably something better to go for. Chi-square just has degrees of freedom, whereas gamma has alpha and beta parameters. So I'll probably try figuring out if, to see if I can find a good fit or not at some point as part of this class. We can do it as part of this class even. All right, let's also go over some recent homework to make sure that we're feeling comfortable with this stuff. This CDF method is a really big deal to me. Yeah, there's the PDF method based on a theorem in the book, which is some of you have just done the PDF method because it was quicker. But I really want you to know the CDF method because it's, well, to me, for one thing, it's less confusing once you really understand it. And for another thing, it really sort of, you see why it works better than that PDF formula with the derivative. Thought it'd be good to start with problem from the assignment you turned in on Tuesday. By the way, the assignment you turned in on Tuesday, I am almost done grading it. I'm just not quite completely done. So I don't have it ready to turn back yet. I may not be able to turn it back today because I have a little minor surgery that I got to have today, this afternoon. So I'm not sure if I'll be able to get it done or not. Thinking of this problem, look, 78 here. Let z be a standard normal random variable, and let y be 2z squared minus 1. Find the density for y. One of you, I think it was Noah, used the fact that z squared is chi-squared, which is fine. But I wasn't necessarily thinking that you'd have to do it that way. Z is standard normal. Remember, we talked about this. Z squared would be chi-squared with 1 degree of freedom, to be more specific. But let's use the CDF method again. So y is 2z squared minus 1. Z is standard normal. Y is 2z squared minus 1. we want to ultimately find the PDF for y. We want to use the CDF method to find the PDF, because I think it promotes understanding, whereas the book's formula involving the derivative of the transformation, it's just a little bit more mysterious. It's like sometimes quicker, but more mysterious. CDF for y, capital F sub y of little y. We want to find first, and then we want to differentiate it to find the PDF. As I've said over and over again, this is always the probability that the random variable, the capital letter, is less than or equal to whatever the little letter is there. Okay. The capital letters are random variables, abstract ideas, you might say. To be technical about it, they're functions, but we just treat them as intuitive abstract ideas. Makes sense, intuitive abstract. I don't know if that makes sense to put those words together. And the way you do it is you want to relate it to the PDF of Z, or the CDF of Z. Z is standard normal. So this would be one of those situations where I'd want to use that capital phi notation, or I could at least, not that you have to. But we do technically need to be careful here because Z can take on positive or negative values as well. That's another trick here. Makes this a little trickier. Probability that Z squared is less than or equal to 1/2 y plus 1/2. Take the square root, but because Z can be positive or negative, when I take the square root, I really should think in terms of the absolute value of Z. Oops, square root symbol. There. The square root symbol on the right side of the inequality implicitly means positive square root, but Z itself could be positive or negative. And so I really want to say its absolute value is less than or equal to the square root on the right. Which means Z itself, this is good practice for real analysis if you haven't had real analysis yet. Absolute value of a number is less than or equal to another number. That means the number itself is between the opposite of this number, the square root of 1/2 y plus 1/2, and that number itself. The absolute value of A is less than or equal to B, where B is implicitly a positive number. That means A itself is between negative B and positive B. And this is really the difference of two CDF values. Capital phi of this minus capital phi of that. Or if you prefer, like I did when I derived the fact that Z squared was chi-squared with 1 degree of freedom, you could use the symmetry of the normal curve. Symmetry. To say this is 2 times the probability that Z is less than or equal to the one on the right. And in terms of, I made a mistake there, sorry. 2 times the probability that Z is between 0 and that number. And in terms of the CDF of Z, the standard normal, that'll be capital phi of the square root minus capital phi of 0, but we know by standard normal distribution that that's 0.5. Since Z is standard normal. The CDF value at 0 would be 1/2, right? Half the probability under the standard normal curve is to the left of 0. It's symmetric around 0, the PDF. Bell-shaped curve centered at 0. And then distribute the 2 through it back through, and you can write this as 2 times capital phi. I'm going to write the square root now as a 1/2 power, because I'm going to differentiate. And then 2 times a half is 1. So this is a formula for the CDF of y, which again is 2z squared minus 1, in terms of the CDF of z. And again, we only use this capital phi notation for the standard normal distribution. And you don't have to use it. You could call it f sub z instead, capital F sub z. But now we differentiate it to find the PDF of y. So we need to use the chain rule. And we're going to get another derivative. The derivative of the inside is going to be 1/2 y plus 1/2 to the negative 1/2. Then we use the chain rule again and get another 1/2. One of those 2's can cancel. You can ultimately write this as 1/2, okay, 1/2 y plus 1/2 to the negative 1/2, which of course I could also put in the denominator as a square root. I'll write f sub z of 1/2 y plus 1/2 to the 1/2, where f sub z is the PDF of a standard normal, which I don't think has a standard notation, not like a lowercase p. But the PDF is something we can look up. The CDF, the capital phi, has no standard formula. A non-standard formula for capital phi involves ERF, right? The error function. Integral of the PDF of the standard normal involves ERF. It's just notation for the CDF. But the PDF does have a formula. That one. So I got to replace x. Well, I'm replacing mu with 0 and sigma with 1, which makes it simpler. I replace x with that square root. And I'm going to end up squaring it, so the square root's going to go away. There's also a square root of 2 pi down here. Sigma is 1. I'll go ahead and write it with exp. Exp, negative 1/2. The square root's going to go away. You're going to have a 1/2 y plus 1/2 in here. You could also write that as y plus 1/2. What's the domain here? Just think, we haven't thought about the domain yet. What's that? Did I forget the 2? Oh yeah, I forgot that. Sorry. Yep. Okay. I forgot this. Yeah. Okay. Put that in there. Sorry about that. Domain. Domain is important, as we're learning in this class, right? Piecewise functions, domains. You learn about it in pre-calculus. You wonder, why do I care about piecewise functions? Well, in case you take prob and stats for this class, that's why you care. And there's other applications too. Z is standard normal. Values of z, little z, could be any real number in theory. But values of y can't, because they're values of z squared times 2 minus 1. Can't get less than negative 1. Y is greater than -1. It's not a big deal if you put greater than or equal to or just greater than, because it's a continuous random variable. This is for y is greater than or equal to -1. Yeah, don't forget this part here. Is this a familiar PDF? Maybe you didn't look it up. I looked it up and I see it's actually almost familiar. Almost. It seems to be almost a chi-squared. With how many degrees of freedom? 1 degree of freedom, actually. Maybe that makes sense. Z squared was chi-squared with 1 degree of freedom. This is a linear transformation of z squared. It's 2z squared minus 1. Yeah, it makes sense. It should be related to the chi-squared with 1 degree of freedom. The 2 with the little gamma would be 1, so you'd have 2 to the 1/2. That's analogous to the square root of 2 there. The square root goes over the pi as well. The other 2 in the pi will match capital gamma of 1/2, I believe. I think capital gamma of 1/2 might be just square root of pi. So that extra 2 is maybe not clear where that comes from or where that goes. Capital gamma of 1/2 is just square root of pi. So the extra 2 here might be related to the fact that in here we replaced x not with y or y plus 1, but y plus 1 over 2. Maybe that's where the extra 2 down there comes from as well. And yeah, this part here, the x gets replaced by 1/2 y plus 1/2, and little gamma is 1. 1/2 minus 1 is -1/2. So it's kind of like a transformed chi-square with 1 degree of freedom. Not exactly chi-square, but a transformed chi-square. Let's do some simulation with this as well, just to re-emphasize some simulation ideas. So I could do something like this. I could do Z data. RandomVariate normal distribution 0, 1. Do 100 times, say. Never have 100 observed values of a standard normal. I'll suppress the output. And y data, well, I need to define my transformation here. 2z squared minus 1, maybe I should call that h of z. 2z squared minus 1. Y data, to obtain that from z data, I want to apply that function to all the z data values. Map h over z data. None of those numbers are less than -1, though many of them could be close to -1. We could make a histogram of the y data. Hopefully it looks like some sort of shifted chi-squared. It should be right skewed. It should go down toward -1 though. Well, maybe I don't have enough data to see that. Okay, you can see it goes negative here. And yeah, that's around -1 there. The origin's not in the usual place, this vertical axis. See if I can force it. There we go. Maybe we do 1,000 data points. Or how about 10,000? but I want to suppress the output so I don't have to see it. There we go. Chi-squared with 1 degree of freedom. What does its PDF look like? Does it have that kind of shape? So this one's not going down towards 0 near -1, right? It's a large tall bar there. If you plot the PDF, a chi-square distribution with 1 degree of freedom as a function of x, does it go up first and then down, or does it just go down kind of like just an exponential decay? 1 degree of freedom, it goes down like an exponential decay. If it's a higher number of degrees of freedom, like 10, it'll go up first, I think, yeah, before going down. Even 2 degrees of freedom does that. Well, maybe 3 degrees of freedom does it. 1 degree of freedom doesn't. Very steep there. It doesn't have a vertical asymptote, but it's close to having a vertical asymptote. Does have a highest value. Okay. How about limit? Okay. Yeah, I'm pretty sure it has a highest value. Maybe I'm wrong there. Yeah, I think I probably am wrong there. Actually, probably does have a vertical asymptote is what I'm trying to say. Anyway, the histogram will not have a vertical asymptote. Histograms can't have vertical asymptotes, but it's decreasing and shifted to the left. Does it make intuitive sense that would happen? You think about a standard normal distribution, there's the PDF, standard normal. Simulated data values are going to cluster close to 0. Every once in a while, not. But they'll almost all be between -3 and 3. The transformation, think of this as a z-axis here. And think of this as a y-axis. The transformation y equals 2z squared minus 1. If you graph it, it's going to be a graph that looks like a parabola opening upward, about like this. That's not a PDF, not a CDF, it's a transformation. I'm trying to imagine transforming the data values on the z-axis horizontal to corresponding data values on the y-axis is what I'm trying to do. Points close to 0 for z will get mapped close to -1. Plug into the red function, that function, you'll get close to -1. That's why there's so many values close to -1. Points a little further away will get mapped to points a little further away from -1 if you're further away from 0 on the z-axis. Points really far away over here could get mapped to positive values of y. But that's going to happen less often. The data along the transform data along the vertical y-axis here is going to cluster close to -1. That's what we saw in the histogram. Although y was horizontal with the histogram. In this picture, it's vertical. This kind of picture can give intuition. The green graph is a PDF, the red graph is not a PDF. Red graph's a transformation. Imagining data being transformed from the horizontal axis to the vertical axis. I think it's pretty cool to think that way. All right, let's also spend a little time, maybe even a lot of time, talking about the homework due today. Although I do want to try to go as quick as I can. I did work before class on making a solution key for your homework due today. In Mathematica. So x and y are independent random variables where x was uniform on the interval from 0 to 1 and y was exponential with parameter beta equals 1. And beta would be the mean. So the mean of y is 1. Use the CDF method to find the PDF for the maximum of x and y. And it's tricky, it's piecewise. Got to think carefully. Let's look by hand first. V is the maximum of x and y. That's the transformation. The derivative formula from chapter 4 would not work here. It would not be helpful. You got to use the CDF method. Because well, the transformation it's actually a transformation of 2 variables instead of 1, for one thing. And it's a maximum. How do you differentiate a maximum? Can you? You got to use the CDF method. Capital F sub capital V of little v. Always matching those variables. Make one a capital letter, make one a lowercase letter. It's the probability that capital V is less than or equal to little v, which is the probability that the maximum of x and y is less than or equal to little v. Which means if the maximum of 2 quantities is less than or equal to some other number, then both of them have to be. X is less than or equal to little v, and y is less than or equal to little v. And here's where you use independence. Assuming x and y are independent, we can use the multiplication rule for independent events, since x and y are independent. We're making that as an assumption. When you're doing simulations, if you simulate them separately with RandomVariate, that will automatically be true. RandomVariate is simulating them independently. So by the way, here are 2 examples of non-independent variables. Z and y are very dependent. If you know z, you know y. But here, x and y are independent, I'm assuming. Could I assume they're dependent? Yeah, I could make various kinds of assumptions of dependency, like maybe a direct relationship between them, but that's not so interesting and maybe not so clear what to do if you did. Now use the CDFs of x and y individually, but you got to be careful about domain. X again is uniform 0, 1. Y is exponential with a mean of 1. X has to be between 0 and 1, but y can be any positive number. Just because its mean is 1 doesn't mean it couldn't take on a value of 1,000,000. That would be extremely unlikely, but theoretically possible. The CDFs for x and y are which are what these are. You could write, you don't have to write this, but you could say this is capital F sub x of little v times capital F sub y of little v. Keep the little v consistent. Technically, these are defined for all v, but with x, it's only something non-trivial when v is between 0 and 1. All right, capital F sub x, I'll use a little x here, is, well, if I want to be fully thorough here, 0 if x is less than 0, leave some space and write a 1 if x is greater than 1. and something else if x is between 0 and 1. What is the something else? For the CDF of a uniform 0, 1. It's very simple. X. Graph looks like this. Zero, when the output's 0, you're going to get 0 there. When v is 0, the answer is 0. You don't have to bother with that case, but you do need to think about these two cases separately. And they're going to affect the answer. The answer is going to be piecewise here. When v is between 0 and 1, the output of f, capital F sub x, is just the input, v. When v is between or greater than 1, then the output of f sub capital X is 1. CDF of y, which is exponential with mean 1, I hope you were able to figure out to be, if little y is positive, at least capital F sub capital Y of little y ends up being 1 minus e to the negative y. That's something you had to figure out. The PDF is just e to the negative y. CDF is an integral of that, but not any old integral. It's got to be this one. Not any old antiderivative. This one has a limit as that y goes to infinity of 1. And a limiting value as y approaches 0 of 0. And that stays the same, but use a v instead of a y. It's the same in both cases. So there's the CDF of capital V. Differentiate it now to find the PDF. Making the PDF piecewise as well. Now, technically speaking, the PDF is not differentiable at 0 or 1. While capital F is continuous at 1, it's not differentiable there. If you graphed it, you didn't have to graph it, but I did. If you graph it, it looks about like this. And then it's got like a corner there. That's what the graph of this function looks like. And there's a lack of differentiability at 1. But it's not a real big deal just as a single point because you're going to integrate little f and single values don't matter. Integrate it at least if you want to find the mean. Here we're just after, well, integrate v times it if you want to find the mean, which you do later on. Just differentiate this. I need the product rule with the second thing. And the chain rule, and it looks like I get that, and then I get this. And I believe the graph of this PDF ends up looking about like I'm not sure if it starts at 0 or not. Does v goes to 0 or does this go to 0? Yeah, okay. I think it looks something like this with jump discontinuity at 1. And in fact, you could even say open circles at both spots. It's highest just less than 1. The data are most dense just less than 1. And they get less dense just bigger than 1, a lot less dense. if you did when you do simulations. In my solution key, I defined the CDF of X. I differentiated to find the PDF of X. That was the uniform 0, 1. Here is the Y, which has exponential with mean 1. And here I did V and W's, CDFs. That's V, the maximum. W, you need to use the, that's the minimum. You need to use the addition rule, which is essentially what that equation is doing. Y. W is the min of X and Y. It's CDF, as always, is this kind of thing. But now for the min to be less than or equal to a given number means or X or Y is less than or equal to W instead of and. But then you can use the addition rule. That's the same as the probability that X is less than or equal to W plus the probability that Y is less than or equal to W minus the probability that X is less than or equal to W and Y is less than or equal to W. And then with this one, you can use independence and write it as a product. So that's what I did here on that line. Then I differentiated them to find their PDFs and I made graphs. The one on the left is for the maximum. The one on the right is for the minimum. Minimum's got to be between 0 and 1, by the way. X is uniform 0, 1. It never goes bigger than 1. Y could be bigger than 1, but you're taking the min, so you're never going to get a min bigger than 1. So the domain of W is 0 to 1. These calculations compute the means and second moments of V and W, both as in exact form and approximate form. So the exact first moment, the mean of V, I guess this is just V, excuse me, is that, and its approximate mean is 1.13. The exact second moment, not variance, second moment of V is that, it's exactly this. Then this is computing the variance. Take its square root, this is the standard deviation. Same kind of thing for W here. Okay, so you should have, for V, a mean of about 1.13, standard deviation of about 0.92. For W, mean of about 0.37, standard deviation of about 0.27. As far as number 4 went, simulating with RandomVariate, there's various ways I think you could have done it. Here's the way I decided to do it. So I used RandomVariate with uniform distribution and exponential distribution to generate X data and Y data. And then I found V data and W data this way. I used table, and maybe there's a way to do this without table, or maybe you just did something different. Table generates lists. I'm taking the maximum values of corresponding X data and Y data values as I, the iterator for the location of the X and Y data, goes from 1 to 100, and generating then a list of V data, maximum data, doing something similar with minimum. And then I do mean, standard deviation for both of those. And every time you enter this, you're going to get a different answer. But approximately, the mean of V here for this run, okay, close to 1.11, close to that 1.13. Standard deviation, 0.88, close to hopefully 0.92. Yeah, not too far. For the minimum, mean 0.35, close to 0.37. And standard deviation 0.29, close to 0.27. Okay. Again, there's probably, you guys probably did this in a different way if you were able to do it. That's the way I chose to do it. Not going to go over the deductible problem, but I believe if I need to double check things, but I believe I got a mean, well, I got a mean of 818.7. So if you got that, does that sound right? Did you get that now, or you have a question?
I just have a question. You integrated from 0 to 1. And I was finding when I did that, I got the same simulation. But I was just curious why it doesn't continue past.
Because the minimum will never be bigger than 1, since x is never bigger than 1.
Oh.
So if you got 818 for the mean of y for the deductible problem, that's what I got. I'm not positive it's right yet. I need to double check things. The CDF has a discontinuity at 0. The CDF value at 0, I got to be 0.18. So if you got that, that's good. It's the same as the probability that x is less than 200. So you have to integrate the exponential distribution to find that. X is exponential with a mean of 1,000. So its PDF is 0.001 times e to the negative 0.001x. Integrating that from 0 to 200 gives you the probability that x is less than 200, which means the insurance payment is 0. The deductible is the only thing the person pays, and insurance pays nothing. All right, we got about 17 minutes left. Let's do one new thing then. I think it was worthwhile to re-emphasize all those things. Today, let's do one new thing. And let's do another insurance application. This time, instead of a deductible, let's say the policy has a maximum payment. So X is once again the loss of the person, like in a car accident. Let's, like in the homework problem, assume this is exponential with mean of 1,000. Exponential with mean equals 1,000. Mean is same thing as the beta for an exponential distribution. Its PDF is 1 over beta, e to the negative x over beta. This time, y was still the insurance payment, but instead of there being a deductible, there's a maximum payment. The insurance wants to cover themselves in case you have $1 million loss and not pay $1 million. Now, of course, a car is not going to be worth $1 million unless it's some crazy collectible. But there's no deductible. Let's say they pay X if, oh, for example, X is less than 2,000. But they never pay more than 2,000. So once again, y is a piecewise function of x. With deductibles, it was 0 in the first spot and x minus the deductible in the second spot. With a maximum payment, a cap, it's called capped insurance. It's x in the first spot, whatever the loss is, as long as the loss is less than the cap, and then it equals the cap or the maximum if x is greater than or equal to the maximum. I could call this function h of capital X if I like, or I guess I should call it capital H to be consistent. And Certainly to find the mean of y, it's actually easier than thinking about the CDF and PDF. You can use the generalized expected value formula for a function of the original random variable. In the general case, that's going to be this, where this is the PDF of x here, not y. And for our situation, when x is exponential, it's going to be an integral from 0 to infinity, you might say, but also because h of x takes on a constant value of 2000, once x reaches 2000, careful, we aren't going to get one integral though, we are going to get two integrals. The integral from 0 to 2000 of x times the PDF of x. PDF of x exponential with mean 1000 is going to be 0.001 e to the negative 0.001 x. But then I have to add the integral from 2000 to infinity of 2000 times the PDF. 2000 times 0.001, I'm running out of space here, e to the negative 0.001 x. Right? I am integrating h of x times f, but I can split that into two pieces because the h function is piecewise. This one you'd have to do integration by parts to do it by hand. This one you wouldn't. For the sake of time, let's just have Mathematica do this. Think about it intuitively. The mean of x itself is 2000. The integral from 0 to infinity, oh no, 1000, sorry, 0.001 times e to the negative 0.001 x. Okay, this is just the PDF, so this integral is going to be 1. Oops, forgot my negative sign. Integral of x times that is going to be the mean, 1000. But our mean for y, this capped insurance, is the integral from 0 to 2000 plus the integral from 2000 to infinity, where this is an x and this is a 2000. It's got to be less than 2000. That. The mean of x, it's got to even be less than 1000. The mean of x is 1000. The mean of y is less than 1000. Because you're not going to have, x could have very high outliers. Y is not going to have very high outliers. It never gets bigger than 2000. So it should be intuitive that its mean is smaller. And we can simulate. I won't take the time to do that. Let's instead find the CDF of y and wonder whether whether it might be discontinuous again. You don't have to find the CDF and the PDF for the mean. That's nice. But it's interesting to still find the CDF and the PDF. The PDF, it's going to be a mixed random variable. So the PDF is not something you can easily describe. But the CDF is definitely possible to describe. CDF of y. Think about it intuitively here. Well, it's the probability that capital Y is less than or equal to a given little y. Once little y gets to 2000 or above, the probability is 1. X could be bigger than 2000, and the probability that x is, for example, less than 3,000 is not 1. Close to 1, but not equal to 1. But y never can get bigger than 2,000. So if I put a 2,000 there or anything bigger, it's a guarantee. 1 is the probability. Like the harder part is when y is less than 2,000. But this is actually easier than the deductible, because y equals x if x is less than 2,000. Capital Y can be replaced by x if the number to the right, now I'm calling y, is less than 2,000. With a deductible, it was in the case where x was bigger than the deductible, you had to replace y with x minus the deductible, and you had to add the deductible to both sides of the inequality, and it was a little trickier. This is a little easier. Y, capital Y equals capital X if this number is less than 2,000. And so then you just need the CDF of capital X and plug in Y instead of little x. And let me reorder these. And that'll be 1 minus e to the negative 0.001 times little y. It's a piecewise function. Is it continuous? No, it does have a discontinuity. Well, let me also add 0 if y is negative. Sorry, this is not very clean homework. I was assigning this to myself as homework. Where's the discontinuity? Is it 0? No, the discontinuity is at 2,000 this time. It's at 0 for the deductible insurance. It's at the cap for capped insurance. Graph of capital F sub capital Y can be 0 over here. This does have a limit of 0 as y goes to 0, because e to the 0 is 1. 1 minus 1 is 0. But as y approaches 2,000 from the left, this does not approach 1. Does it approach? Replace y with 2,000. 001 times 2,000. E to the negative 2. Not 0. 1 minus that is not 1. It's about 0.865. And technically, I should be careful about where's the open circle and where's the closed circle here. At y equals 2,000, we jump up to a probability 1. So the closed circle should be up here. And there should be an open circle there. That's what the graph of the CDF looked like. The PDF is going to look like an exponential decay, except then jump down to 0 when you get to 2,000. Technically 0 over here as well. What is its value at 2,000, not 20,000? What is its value at 2,000? Well, technically speaking, you should really say it's undefined, right? This is not differentiable at 2,000. However, that can be problematic in terms of the more general theory, actually. In effect, you end up saying it's infinite at 2,000. In a sense, there's an infinite jump there, infinite slope, you might say. But it's not any old infinity. It's an infinity that makes the PDF integrate to 1 when you integrate it from 0 to 2,000. If you only integrate this part from 0 to 2,000, you're actually not going to get 1. You'll get 0.865. In effect, the value of the PDF has to be infinite at 2,000 in such a way that when you integrate to including past 2,000, the integral is 1, as it has to be for a valid PDF. And to get into what this means and how you do it, it's again, beyond the scope of this course. Theory of distributions, generalized functions, Dirac delta function. Most of you never heard of that probably. Okay, but you actually can make it rigorous, but we're not. Some people don't, that's supposed to be an infinity, by the way. Some people don't say it equals infinity there. Some people put a finite value. They put 1 minus 0.865 in this case. Wherever that is on here, I don't know where it is. But that is sort of a misrepresentation of what the PDF in this kind of context means. This part you'd integrate to find probabilities, but the part over here you'd plug in a value instead of integrating. So it all gets confusing, but don't worry about it. I'm not going to test you on the PDF of this. I could have tested you on the CDF. Okay, but again, to find expected values, you can always use the PDF of X, so it's easier. You don't have to find the PDF of Y. All right, have a good day.